everybody, welcome back to Monte Carlo methods. When we last left off, we were talking about the accept-reject method, which is generally used to simulate from a continuous one-dimensional distribution. It can certainly be used for discrete distributions, but I don't think it's usually worth the hassle of the extra steps that you need to consider to run accept-reject when we have other methods for discrete distributions, such as interval chopping or distribution-specific methods that we've talked about, say, for the geometric distribution, but it can be used in the discrete case. It can also be used for higher dimensional distributions, but the accept-reject algorithm becomes difficult to work with kind of quickly. You may recall one of the first steps is that you have a target PDF that you want to simulate from, and one of the first steps is to come up with another function that is an upper bound for that, and that alone can be tricky in higher dimensions. However, I have used it in 2 and 3 dimensions, and if you have no other choice, then you might as well. But generally, continuous random variables and one-dimensional random variables at that. So today's video, I want to actually try the accept-reject algorithm on an example, and because there's pitfalls, there's specific things I want you to look out for. So let's start off by a quick review of the algorithm. Suppose I want to simulate a random variable x with a PDF f. This is the target PDF that we want to simulate from. I'm going to let S be the support for F. This is the place where the PDF is interesting and non-zero. For an exponential PDF, this is 0 to infinity, whereas for a uniform 0-1 PDF, this is the interval from 0 to 1. The next thing you need to do in theory, because you'll see today in practice that I don't actually follow this usual typically given order for these steps, but in theory, the next thing you need to do is to find a function g that is an upper bound for f. At least you need g of x to be greater than or equal to f of x for every x in the support for the distribution. If it's not greater outside the support, that's fine. The next thing you need to do is to be able to integrate the function g over the support s, and you need to get something finite. Now, g is greater than or equal to f, and f is a PDF, so I know that g is greater than or equal to 0, and it's going to integrate to something greater than or equal to 1. So if I integrate this, I'm going to call the value c. It would be a problem if this was 0, but that's not an issue because the integral is greater than or equal to 1, and I do need it to be finite. So if that happens, then you define a new PDF. I called it h, and this is just g that has been renormalized by c. It's been divided by c, so now it integrates to 1. So h is greater than or equal to 0, and it integrates to 1, and it is a PDF. Now, if that wasn't enough for setup, you need to be able to simulate values from h. At this point in this course, the only thing we have is the inverse CDF method. You will be getting some more things for your toolkit, but this is a big if. There's several big ifs in setting up the accept-reject algorithm. However, if you can do all this stuff, then it's very easy to run. Number one, you need to generate a value, a random variable, or an observation of y, a random variable with PDF h. And then you need to generate a random variable u, uniform 0-1, simply using your random number generator. Now, when you generated y, you probably used uniform 0-1s from your random number generator. For example, if you use the inverse CDF method, and this uniform needs to be a new one and independent of anything you use to generate y. So overall, we want this u to be independent of this y. Now, if u is less than or equal to f of y over g of y, and by design, this ratio is less than or equal to 1, then you accept this value y as a draw from your target distribution. And I set it up with, I want to simulate a random variable x from the PDF f. So at this point, I would set x to be y and exit the algorithm, and I would have a single draw from the target PDF f. If this u is not less than or equal to this ratio, then you throw everything out. You throw out the u, you throw out the y, and you start over up here with independently generated values. And you keep going until you get one acceptance, and that gives you a single value drawn from the target distribution. So for today, I would like to illustrate this for the gamma distribution, and I'm going to spend a little time reviewing the gamma distribution. I'll try to remember to come back here and put a timestamp in case you want to skip this part. But the continuous random variable x has a gamma distribution with parameters alpha and beta. They both need to be strictly positive if x has the following PDF. I'm about to write down a PDF, and you might say, no, that's not what I use. This sometimes is parameterized differently. So I'm going to say that the PDF is 1 over gamma of alpha. This is something known as a gamma function, and I'll talk about this in a moment. Beta to the alpha, x to the alpha minus 1, e to the minus beta x. Whenever x is greater than or equal to 0 or strictly greater than 0, it doesn't matter. And the PDF is going to be defined to be 0 otherwise. Now, you may have 1 over betas in place of my betas. And this is just like our discussion about how I parameterize the exponential distribution a few videos back. I write my exponential distribution as a lambda e to the minus lambda x. You might have seen 1 over lambda e to the minus x over lambda. In my case, lambda is known as a rate parameter for the exponential distribution. And if you do it the other way, it is a mean parameter. And that's the same thing going on here. It can be parameterized differently. But I'm going to write x squiggly line has the distribution gamma of alpha comma beta when I mean that x has this PDF. And you might use this notation for a slightly different PDF, and that's okay. So this gamma alpha comma beta is the name of the distribution, whereas this gamma of alpha is something entirely different. Let me write that down. Gamma, the capital gamma with 2 parameters inside, is the name of the distribution, and the capital gamma with a single parameter inside is something known as a gamma function. The gamma function, gamma of alpha, is defined to be the integral from 0 to infinity of x to the alpha minus 1 e to the minus x dx. And why do we care about this, and why do we have it in front of the PDF? Because check this out. I'm going to integrate from 0 to infinity beta to the alpha x to the alpha minus 1 e to the minus beta x dx. Now, this is the gamma PDF that I gave you without that gamma function part. This is the rest of it. And I am going to group together the beta and the x. So I'm going to write this as the integral 0 to infinity of beta and x to the alpha minus 1 e to the minus beta and x. And then I have an additional beta that I'm going to put over here with the dx. I'm now going to make a u substitution. I'm going to let u be beta x, and then du is beta dx. And because beta, the beta parameter, is strictly greater than 0, I do know that if x goes from 0 to infinity, u defined to be beta times x does also go from 0 to infinity. So I get the same limits of integration. But now look at this. This is gamma of alpha. And so if you look up here, this is the gamma PDF missing 1 over gamma of alpha. If you put 1 over gamma of alpha right here, then this whole thing will integrate to 1. So the 1 over gamma of alpha, this is just part of the constants that go in front of the PDF to get it to integrate to 1. Nothing more than that. So again, before going on to the accept reject algorithm, I'm still talking about the gamma distribution, and I want to talk specifically about some properties of the gamma function. It has so many cool properties. I'm only going to talk about 3 today. One is that gamma of 1 is 1. This is super easy to see. If you plug in 1 up here, you get the integral from 0 to infinity of e to the minus x dx, which is 1. I better not catch you integrating that. This is an exponential rate 1 PDF, so we already know it integrates to 1. The second property for today, again, there are many more, but for today, if alpha is greater than 1, so this is a real valued parameter, and if it's greater than 1, then gamma of alpha is equal to alpha minus 1, gamma of alpha minus 1. I'm going to get you started on how to do this, and that is with integration by parts. So you'll recall that the integral of u dv is u times v minus the integral of v du. In this case, take u to be x to the alpha minus 1 and dv to be e to the minus x dx, and go. At some point, you will find yourself with an x to the alpha minus 1 e to the minus x that you have to evaluate from 0 to infinity. And when you're evaluating at infinity, that's like taking the limit as x goes to infinity. And although when alpha is greater than 1, x to the alpha minus 1 is blowing up, the e to the minus x is eventually going to take over and bring it down to 0. So the limit as x goes to infinity of x to the alpha minus 1, e to the minus x is 0. And you can show this using L'Hopital's rule. And this is going to be part of what you'll have to deal with when you carry out this integration by parts. But otherwise, it's not too hard to show that gamma of alpha is alpha minus 1 and gamma of alpha minus 1. So the third and final property for today is that if n is an integer greater than 1, then gamma of n is n minus 1 factorial. So an integer greater than 1, this is just a special case of an alpha greater than 1, which was a real number. So I can use the property 2 that we just talked about to say that gamma of n is n minus 1 times gamma of n minus 1. But I can use property 2 again on gamma of n minus 1 to say that it is n minus 2 gamma of n minus 2. And if I keep sort of bringing down the argument of gamma in this way, I will get n minus 1 times n minus 2 all the way down to 1 times gamma of 1, but gamma of 1 is 1. And we're left with n minus 1 factorial, which is what we wanted to show. So I know you want me to get on to the simulation algorithm. Just one more thing I want to say, and that is the alpha parameter here is known as a shape parameter. So let's look at the x part of this function and ignore the constants out front because it really is just a constant. I want to look at graphing something like this. And if you multiply that all by a constant, that's not going to change the shape. If you look at x to the alpha minus 1, e to the minus beta x, and you imagine that alpha is greater than 1, then we have x to a positive power, e to the minus beta x. So when I plug in x equals 0, I get 0. And then the x to a positive power is making this thing increase until the e eventually takes over and brings it back down. When alpha is greater than 1, we get a shape that looks kind of like this. And this lump can be higher and lower and flattened out and mushed out more towards infinity, but this is the general shape when alpha is greater than 1. When alpha is equal to 1, then x to the alpha minus 1 disappears. We just have e to the minus beta x, and that is an exponential distribution. In fact, the constants do work out correctly because they have to. If this is going to integrate to 1 when alpha equals 1, and I have e to the minus beta x, the rest of the stuff had better turn into just beta because that would be the exponential rate beta PDF, beta e to the minus beta x. And in fact, when alpha is 1, beta to the alpha is that beta, and gamma of 1 is 1. And so we do get the PDF is beta e to the minus beta x, which is the PDF for the exponential distribution, which looks like this. And finally, when alpha is between 0 and 1, then the x to the alpha minus 1 is like 1 over x to a positive power, and the PDF does blow up at x equals 0. So it asymptotically approaches the y-axis. So these are the three general shapes you can get, and they are governed by the shape parameter. I really need to get back to the algorithm, but the beta parameter, as I have written it, is known as an inverse scale parameter. And if you write 1 over beta in place of my beta, then it's known as a scale parameter, and it just rescales things. But yeah, this is a simulation course. So let's get back to the accept reject algorithm. As an example, I want to use it to simulate from a specific gamma distribution, namely the gamma distribution with alpha equals 3 and beta equals 2. So if you write this out, the target PDF is 4x squared e to the minus 2x. This is what I want to simulate values from. You'll recall there are these steps: find a function g, be able to integrate it, etc. And this is not the way to run this algorithm. I did give you the steps in this order. This is how it's usually given, but not the way to run this algorithm, because you'd be not even surprised at how many times you'll set up a g and you'll go and you'll say, oh, I can't simulate or draw values from what I got for h. What I would highly recommend is starting with h first. So I want to kind of work backwards here by choosing h of x first. So this is the target, and I want something I can simulate from. And I'm kind of thinking ahead about that ratio f over g, which is essentially f over h with the constant put in there. And I would like that to simplify. So I'm looking at this e to the minus 2x, and I'm thinking, that's almost an exponential distribution. I know how to simulate from that, and that'll give us some cancellation. So let's try letting h of x be e to the minus 2x, but then I need to multiply by 2, so it's a valid PDF. This is an exponential rate 2 PDF. And h was defined to be g over c, but we've yet to define g. Well, g is c times h. So how do we find that c to define the g? G is c times h, and this needs to be greater than or equal to f of x for all x, in this case, greater than 0. So I want to find a c that is an upper bound on f over h. I'm going to call this ratio r of x. I'm using r for ratio. And if I look at this f over this h, I'm left with 2x squared. And this is bad news because this is unbounded and increasing, and I cannot bound it with some c. This means I did not choose h wisely. I'm going to stick with my idea that I would like it to be an exponential distribution just because I know how to sample from that kind of easily. I know how to simulate values. So looking at what I would like to have in this ratio, I have this x squared going up, I would like an e to a negative power, bringing it back down so that it's bounded. The top of the ratio is going to have an e to the minus 2x. I would like something in the bottom that overall would leave me with an e to a negative power. And what this means is I want h to not go down as fast out in the right tail as f. So people will say, for the accept reject algorithm, you need to choose a proposal distribution that is fatter in the tails. Your f goes up from the x to the 2, and then it comes back down. And the h, the way I'm choosing it, just goes down. But I would like it in the tail to stay above the f. So I am going to try e to the negative x, because when I look at e to the negative 2x over e to the negative x, I'm left with e to the negative x for the ratio, something that's going to bring that x squared here down. E to the negative x is already a valid PDF. It's an exponential rate 1, so I don't need to put a constant out front. Let's let h of x be e to the negative x. I want to find a c such that f over h is less than or equal to c. I'm going to call it r again for ratio. This is 4x squared e to the minus x. I'm going to take a derivative, set it equal to 0. I find two critical values, x equals 0 and x equals 2. X equals 0 is not really in the space. I am looking at all positive x's here, and x equals 2 is in the space. And it's easy to verify using a second derivative or looking at the graph of something like this that it does in fact give a maximum. So I want an upper bound for f over h. I just found the value that I could plug in here that gives me the largest value. I'm going to use that. So my c, my upper bound, I'm going to define to be r of 2, which is going to be 16 e to the negative 2. That is an upper bound for f over h. It happens to be the tightest bound we can come up with, because you can take any value for c that is above the 16 e to the negative 2, but I wouldn't recommend it for reasons that I will show you towards the end of this video. Okay, so here's the algorithm again. I'm not going to drag you through the steps here because I already recapped it at the beginning of this video and talked about it in the previous video, but I did want to point out what changes for our specific problem. This generate y with distribution h becomes generate y from the exponential rate 1 distribution. This ratio I have worked out, f of y over g of y is f of y over c h of y. Here's the f, here is the c, here is the h, and this simplifies down to 1/4 y squared e to the negative y plus 2. So now you have 4 concrete steps to follow. Super easy, and we're not done, but in the next video, I will do an R tutorial video where I actually run this algorithm for you. But I ran it, and I did it 100,000 times. I made a histogram, and I superimposed the true PDF for the gamma 3,2 distribution, and I think it looks great. And the acceptance time was pretty quick. That is what I want to talk about in the remaining part of this video. So for now, let's just marvel at this wonderful histogram with a superimposed PDF. It worked well. But yes, to finish up this video, I want to talk about the rate of acceptance, the expected number of steps to accept. And first, let's start with the question. For the accept-reject algorithm, what is the probability of accepting on any one try? What's the probability that you can go through those steps just once and not have to throw everything out and start again? So the probability of accepting on any one try is the probability that capital U, because I'm trying to compute probability here, so I do need my randomness, is greater than or equal to f of capital Y over g of capital Y. To compute this, I'm going to condition on the value of y. So I'm going to get this probability given that capital Y equals little y. I'm going to multiply by the PDF for capital Y, which is h, and I'm going to integrate over all little y from minus infinity to infinity. This is a more general proof, not the 0 to infinity example that we were looking at. And I'm going to plug in capital Y equals little y over here. And then note that I have a conditional probability left. And the only random thing now on the left side is the uniform U. And the only random thing on the right side of the conditional line is the capital Y. And these were assumed to be independent. So I do get to drop this information because number one, I've used it. And number two, the probability that I'd be computing for U does not depend on the value for Y. Okay, so I'm left with the probability that U is less than or equal to f of little y over g of little y. By design, this is less than or equal to 1. The probability that U is less than or equal to like 0.3 is 0.3. It's equal to the number as long as the number is less than or equal to 1. So we end up with f of y over g of y. G of y is, of course, c times h of y. I get some cancellation. And so we get the probability of accepting in any one try of this algorithm is 1 over c times the integral from minus infinity to infinity of f of y dy. But f is a PDF, and this integral is 1. It's okay if the PDF is 0 for part of it. But in general, when you integrate any PDF, no matter what the support, if you integrate from minus infinity to infinity, you will get 1. I'm left with the probability we accept is 1 over c. So I can tell you right now that c, that upper bound on the ratio, you want it to not be too big, because the bigger it is, the smaller your acceptance probability is. Furthermore, the number of trials to accept has a geometric distribution. We're trying, the probability that we succeed is 1 over c. Otherwise, we're starting all over and trying again. So we have independent trials of an experiment. We've got a probability of success on any one trial. This is how you define the geometric distribution, the one that starts from 1, which I believe is the one I talked about so far in this series, because there's also another geometric distribution that starts from 0. And the expected value for this geometric distribution is 1 over p, which is going to be c. Again, I don't want c to be large because I don't want the expected number of trials to be large. So you want c to be as small as possible. So when looking at the ratio f over h, try to find a least upper bound. So try to actually maximize it as we did using calculus, and don't just take an arbitrarily larger upper bound, which sometimes you're forced to do if you can't work with the function. Sometimes you are able to say, okay, I'm going to take this ridiculously large c. I know that's going to be above where I need to be, so I will work with it, but you'll get really bad acceptance. Another thing is that it generally is better to make your h kind of more closely mimicking your target PDF f. We didn't do that at all here. We just chose an h that we could work with. But yes, as your toolkit gets larger for being able to simulate from a proposal distribution, as you get more flexibility, it would be a good idea to mimic the target PDF as closely as possible. Okay, so in the next video, we are going to talk about simulating from the normal distribution. We could use accept reject, but I've got something even better for you. Actually, before the next video, I will have an R tutorial, but in the next lecture video, it's the normal distribution all the way. Next time on Monte Carlo methods. I hope to see you there.